Hello students, welcome to the Physics 212 and 216 GL Electromagnetism lab, and the topic for our first lab is electric charge. So let's go through the objectives of this lab. The first thing is to investigate some of the properties of electricity at rest, which we call electrostatics, which involves electric charges and the force between them and their behaviors in materials. We also will study the principle of superposition and how to use vector addition to figure out the force between several charged particles, and also to investigate the behavior of the charge distribution of an extended object and discover that the charge can be thought of a series of point particles. So we can model the forces by these objects with the use of the superposition. So the first question is definitely, what is charge? So the electric charge is the physical property of matter that causes it to experience a force when placed in an electromagnetic field. So we can compare this property with mass, which is also a physical property of matter, which causes to experience a force when placed in a gravitational field. So we know that like the mass attracts each other, but the difference with the electric force and the gravitational force is that there are two types of electric charge, positive and negative, but there's nothing such for mass. So the positive charge is mostly carried by protons and the negative charge is carried by the electrons. And object with an absence of net charge is referred to as neutral, which means it doesn't have either of the charges. And a very important concept here is that charge is quantized, so it comes in integer multiples of individual unit called the elementary charge of an electron, which is just 1.6 into 10 to the power minus 19 coulombs, which is very small. So if we have 10 to the power 19 electrons, and their charges will combine into 1.6 coulombs. So it's a very small number. And the law that we use to figure out the force between two charges is called Coulomb's law. And according to Coulomb's law, the force is proportional to the charges and inverse square proportional to the distance between the two charges. And we can definitely equate them with a constant k, which is the proportionality constant. So here we have two charges, q1 and q2. So in the first example, the q1, the red color is positive, and q2, the blue color is negative. So we know from Coulomb's law that the same charges repel each other and opposite charges attract each other. So according to the law, this q1 and q2 in the first picture, they should attract each other. And that's also denoted by the blue arrow here, and which should be proportional to the charge and inverse square proportional to the distance between them r. And in the second example, both the charge q1 and q2 are positive, so the same charge repel each other, and which is denoted by the outgoing orange color vectors. So what's the origin of charge? That is actually comes from the atoms, like which is the fundamental unit of matter. So to visualize an atom, um, just simply it has like two parts, which the center part is nucleus, and nucleus has neutron and protons, where the proton is positive charge and neutron is neutral, so it doesn't have any charge. And we also have electrons in orbits around the nucleus, and electrons have negative charge, which is equal amount of protons. So in a neutral atom, the total amount of charge or net charge is zero, because we have like equal number of protons and electrons in a neutral atom. But whenever this equity between the number of proton and electron is imbalanced, then we have charge. So in the second picture, the first example where the number of protons and electrons is equal, so the atom is neutral. But if somehow it gets an additional electron from a different atom, then it has like more electrons than the number of protons, so it becomes negatively charged in the middle picture. And on the other hand, if the atom loses one electron or give it to another different atom, then it becomes positively charged because it has less number of electrons than the number of protons. So the total charge is positive. So there's a very important concept that can help us to visualize like how the force is going to be around the point charge, which is called electric field. So electric field can be described as some imaginary field lines which um, is caused by some charge. So if we have a positive charge, like the electric field lines are outward, and as we can see, the density of the field lines actually like give the approximation of how much force another charge will experience if it comes near the electric field. So near a point charge, the electric field lines are more dense, but as you go farther away from the charge, the electric field lines get less dense, which means that another charge will experience less amount of force if it's farther away from that charge. So the same way, a negative charge will also create field lines, which is inward to the charge itself. So if we can place two charge, like one positive and one negative, like side to another side, then we would see that the field lines will originate from the positive charge, and then it will get into the negative charge. And the number of field lines actually give the um, amount of the force, and also the direction of the field lines gives us the idea like how the another test charge will experience the force in which direction. So let's start with the first section of our lab, which discuss about static charge and electrical interactions. So when two objects are rubbed together, the interaction causes each to obtain an opposite charge. So this is true for any two objects pressed or rubbed together. Say for example, like a glass rod rubbed with silk is considered to be positively charged, where a rubber rod rubbed with far is considered to be negatively charged. So when two different matter is rubbed against one another, so depending on like the electron affinity of that material, some object will lose electrons and the other object will uh, gain those electrons. So depending on like which has like the more tendency to lose electrons, or which one has the more tendency to grab those electrons, so that really determines which charge we will obtain. When the charge rod makes contact with another object, the rod transfers charge to that object. If the object is a conductor, the object will acquire the same charge as the rod. And the second concept for our lab is called superposition, which is actually the use of the vector addition. Because according to Coulomb's law, the force between each pair of charge is a vector that acts along the line that connects the 2-point charges. The superposition principle allows us to find the total net force acting on any charge due to several other charges nearby. So in order to solve or calculate the force between multiple charges, we have to identify each charge pairs and calculate the force from Coulomb's law acting on the charge of our interest. And then we can simply use the vector addition to find the net force on our test charge. To give it an example, we have two different cases here. So we have on the example on the left, we have a test charge denoted by small q, and we have a collection or assembly of three other positive charges denoted by red colors. So we have to deal with each charge pair separately. So starting from the middle one, we can see the vector is acting along the line that connects these two forces. And for that, as they are like same charge, so they should repel each other. And that's what is denoted by the blue arrow on the right. So similarly, the two other charges around the middle one, I mean the below one and the above one, they also um, give some repulsion force to the our test charge small q, just acting along the line of the vector. So we can see the two other blue vectors that is denoting the force coming from the other two charges to our test charge q. So now we can, as we know that we can split a vector into two components or more. So here, like if we wanna split the vector in two components, say we have a x component and a y component. So the x component of the vectors are denoted by orange lines, and the y component is denoted by the green lines. As we can see, the two green lines are just the two y component of the vector which cancel each other. So all that we have left is what is acted along the x-axis, which is the orange lines. So if we sum just the three component which is acted along the x-axis, we will find the net force acting on our test charge from the assembly of three charges. On the example on the right, we have the similar scenario except that we have three negatively charged objects denoted by blue spheres. So in this case, our test charge is still positive, but the other charges are negative, so we have a attraction force. So the force is denoted by the orange line, which is actually acting along towards the blue charge or negative charge. So similarly, we also have two other orange lines just towards the other two charges that shows the force acting along our test charge small q. So similarly, just like the previous example, we can split it into two components, x and y, and as you can see, the y components cancel each other, so all the force that is remaining is acting along the x-axis on the left. So that is an example that how we can find the net force due to a collection or assembly of charges to our test charge. So the section 3 is about distributed charge. So in case A, we have a charge, capital Q, a positive charge, and we also have a positive charge, small q. Just like to have a comparison with the case B, where the same amount of charge, capital Q, is just distributed along the rod. So the total charge of the rod is capital Q. So we can just simply imagine this rod being a collection of point charges. But the center point charge is not any longer capital Q, but it is way smaller than that. So definitely the force from the central part of the rod is not as big as it was before for the case A, where all the charges were Q. So as we go farther away from the center in the rod, there will be more distance from the our test charge plus Q. So the force will be less, because Coulomb's law tells us that the force decreases inverse square proportional to the distance between the two charges. So as we further go away from the center and go to the edges, those charges will be even more far away from the small q charge. So the contribution for those charges, like for the force, is going to be even less and less. So if we compare with the case A, the case B will definitely have less force acting between them. And the last section is to model for electric charge, where we are given a scenario where we have a spherical ball where the left hemisphere is negatively charged and the right hemisphere is positively charged. And the question is like, what's going to happen when a positive point charge will be brought close to the negatively charged hemisphere? So it's very simple to understand that what would happen, because um, the negatively charged hemisphere will definitely attract the positive point charge, because we know opposite charges attract each other. And similarly, the positively charged hemisphere will repel the positive point charge. So if both the hemisphere were at equal distance from the positive point charge, then these two effects will negate each other. But as we can see from the picture that the negatively charged hemisphere is more closer to the positive point charge, so that will attract more from the repulsion from the other hemisphere. And this example can be more demonstrated in the experimental section, where we will introduce a machine called Van de Graaff generator, where we can generate positive charge to one of the sphere, and we have a secondary sphere which can be induced by the primary sphere. And once the secondary sphere is charged due to the induction from the primary sphere, then the charge will be split among the two hemispheres. So the hemisphere that is like more close from the primary sphere will be negatively charged, and the farther away hemisphere will be positively charged. And we can charge a pith ball to be positive and then bring it close to the negatively charged hemisphere and see how is the interaction between them. So with all these sections, we come to a conclusion that um, charges attract or repel each other, and the force is always acting along the line that connects these two charges. And also the distance between the charge also affects the force between them. As we can see, like if the distance between two charge is doubled, then the force will be 1/4 compared to the beginning. So thank you very much for your patience.